Who's got their notes from last unit? Anybody got them handy? Okay. Last unit's notes. Okay. The first day of calculus instruction, I asked you, what is calculus? Okay, what is calculus? And you wrote down, it's the math of change. Okay? Now, the first unit, we kind of introduced to the building blocks that are going to help us figure out how things are changing. Okay? And we are going to start today with focusing on, and we'll do this pretty much for the rest of the semester, figuring out this first major problem solved by calculus. How do you find the tangent line anywhere on a curve? Or how do you find how quickly a function is changing at a point? Okay? Change. We are now into how quickly are things changing. What do I mean by things? For right now, functions. How quickly is a function going up or going down? Is it going up? How quickly? Is it going up slowly? Is it going up quicker? Is it going down? How quickly is it going down? You got that? So what you're about to learn for the rest of the semester, and literally it's the rest of the semester, is just one major problem. How quickly are things changing? Now, if I gave you some values, like 3 and 15, how can you find out the change from 3 to 15? No, I'd say you just subtract the two numbers. You know, from 3 to go to 15, I added 12. If I said from 15 to 3 this way, I'd say I would subtract 12. Okay? From 5 to 9, I added 4. Subtract the 2, you'd get that. If I went the other way, 9 to 5, well, if you subtract 5 minus 9, you get negative 4. Well, yeah, from 9 to 5, I went down 4. Got that? Okay, good. We would say that there is more change between 3 and 15 because I added 12 versus adding 4. Okay, great. The problem is that there's no real context. And I'm going to give you more information about that value, those values. I'm going to give you an x-coordinate that goes with 3 and an x-coordinate that goes with 15. So I changed 12, but over the course of 6 x's. So it looks like I've gone up 12 over 6 x's. Now I got that 5 goes with an x-coordinate of 2, and 9 goes with an x-coordinate of 3. So I've gone from 5 to 9, that was a change of 4, but over a change of 1. So I've gone up 4 over 1x. Would you answer the same way as you did before? That I've gone up more between 3 and 15 than I have between 5 and 9? No, I would say no. And the way that you can kind of make them apples to apples comparisons is by dividing. 12 over 6 is 2, which means I've gone up 2. It's like 2 over 1, up 2 per x. 4 over 1, 4. I've gone up 4 y's per x. What have we been calculating here? Slope. This is important. Very important. Visually, to tell how quickly things are changing, we can take our points, connect them with a line, calculate the slope, rise over run, y2 minus y1 over x2 minus x1. Here the slope was 2. Here the slope was 4. And the slope gave us the change of the function on average over the interval in this case. Slopes equal change. For the first guy, m equals 2, I'd say on average, f of x is going up 2 y's per x from 1 to 7. Green guy, on average, f of x going up 4 y's per x from x equals 2 to 3. Why don't we do 2 to 6? Please calculate the slope that connects those 2 points. Two, 5, 6, 0. Slope. Rise over run. y2 minus y1 over x2 minus x1. I'm not even going to write them down because you guys can figure it out. There's my slope, negative 5/4 on average. My function is going down 5/4 of a y per x. I didn't really put the up 4 y's. I did up 4's. So my bad about that. Up 4 y's per x. Okay? Negative slopes mean I'm going down on average. My function is trending downwards. Positive slopes, my function's going up. Slopes that would be horizontal, that slope would be 0, right? 0 slope means like, well, I've gone up as much as I've gone down from one point to another, okay? What we are calculating when we find slopes is what we call the average rate of change of a function. The average rate of change, or ARAC, is equal to the slope connecting 2 distinct points on the function. It gives you the average rate of change over the interval that you're talking about, from an x-coordinate to an x-coordinate. Now, we are not going to say in the future slope of the 2 points that are connected. We're going to use a different term to talk about these lines that connect 2 points. And if you recall in geometry, we had lines that passed through a circle in 2 locations, and then we had a line that would just touch the circle at 1 location. Most of us will remember what that line is called. What was a line that just touched a circle at 1 location? Tangent. Okay? Now, who remembers what we called a line that crossed through a circle twice? This is where everybody forgets. A chord is close. So a chord actually is just inside. It's not a line. It's just like going from here to here. Very good. Very good. Very good try. It's actually different than a chord. It's called a secant. Okay? A secant passes through a circle twice. So this is called a secant. We are going to use these same terms from geometry, but with functions. We're going to call a line connecting 2 points of a function a secant. So a slope of a secant equals the average rate of change over an interval. Okay, so all of these lines are called secant lines. Even though it's like, oh, this red line, it passes through 1, 2, 3 points. It's like, whatever. We're just talking about, it connects 2 points that we're talking about. It's a secant. All right. Great. We'll finish off with a couple examples here. I can give you a function, I can give you an interval, and say, how quickly is the function changing, on average, over the interval? Please discuss with your neighbors. What would you do? Plug in 1, plug in 4 is correct. Use my friend, the slope formula. y2 minus y1 over x2 minus x1. Find the change in my y's with context. Okay, it's not just, oh, I changed 15 anymore. I said I've changed 15 over the course of 3 x's. This is the context that we need. So I've increased 5 y's on average between 1 and 4. Let's quickly do these, and then you'll go to lunch. And I'll pause the video. y2 minus y1. Make sure things are aligned. You've gone down in your y's 3/4 over the course of 3 x's. That's the same as 3/12. I've gone down 3/12 of a y per x over the interval from 1 to 4. I'll start like a minute later. Cosine from 0 to pi. Cosine of 0, 1. Cosine of pi, -1. I've gone from 1 to -1. The change would be -2 over the course of pi x's. -2 over pi. I'd say I've gone down 2 over pi y's per x on the interval from 0 to pi. You guys can go. I'll do the last one. Like every day. This is an easy one. This is just 0. I have not increased nor decreased over my interval. So, slopes change. That's the key. Slopes are change. Changing your y's, changing your x's, gives you the change in context. How quickly did we change, on average, over an interval? Great. Calculus concerns ourselves with how quickly are we changing at a point, not over an interval. So, at the point 4, 7, are we increasing or decreasing? Discuss with your neighbors. Now, we should be saying, all right, well, the function's going down, so I'm decreasing, okay? So decreasing. Now, by how much? That is the question that baffled mathematicians until the 1600s, when Isaac Newton, big in physics, also decided to discover calculus as well. And this other guy, Leibniz, was a philosopher who decided to study math in his spare time, discovered at the same time, okay? Now, here's the key. With slopes representing change, what do you think would be the visual representation of how quickly this function is changing at this point? Why don't you guess with your neighbors? What about it, though?
What about the tangent?
Yeah, what about it?
The slope of the tangent?
Oh, okay. All right, so Mr. Corey, if slopes represent change, and we're looking for how quickly we're changing at a point, what do you think we need?
Slope of the tangential line.
The slope of a tangent line. Now, how can we draw a tangent line? You guys can kind of just see how a tangent line can kind of be drawn. Just like with geometry, you got circles, the tangent line just like kind of follows the circle and just kind of nicks it. We can kind of draw a tangent line, okay? The slope of this line will tell us how quickly the function is changing. Go to the next page. We're coming back, okay? So, change in context, change at a point. It's not on average over an interval, it's at an instant. We will call it an instantaneous rate of change. A change at a point is an instantaneous rate of change. I need more space, so I'm going to. The instantaneous rate of change of a function at a point is equal to not the slope of a secant, but now a slope of a tangent. The slope of a line that's just going to nick the function at a point, okay? Now, instead of saying slopes of tangents or instantaneous rates of change, we're going to use another term that I'm going to introduce to you that we are going to be saying very casually in this course after today. It is derivative. This is what a derivative is. You probably have heard of them. I've mentioned them, and we will be studying them Derivatives are just slopes of tangents. It's just instantaneous rates of changes of functions. It's the change of a function at an instant. Now, I gave you a little synopsis of what we just kind of talked about here. Secant line, line that connects two distinct points. Tangent line, line that just touches a function. We'll talk about that in a second. Slope of a secant line, average rate of change. On average, how many y's we've changed over an interval. Slope of a tangent line, instantaneous rate of change. Okay, now, how are we going to find this value? Okay, that becomes the next question. And that's the question that baffled mathematicians for a very long time. Well, there's something that we can calculate, and that's average rate of change. And we have a slope formula, right? Slopes, change. It's like, how can I find the slope of this line? Well, if I use the point 1,3 and 715 and use that slope, would that give me a good approximation for that slope in blue? No, it's horrible. It's bad. It's a bad approximation. No. Too far away. This slope is positive, that slope's negative. Not a good choice here. But like 4 is in the middle of 1 and 7. Well, what if I looked at the points 2, 5, and 6, 0? So if I use the point 2, 5, 6, 0, is this a good approximation for that slope in blue? No. Still not good. But is it better than the one I just had? Okay, yes. Well, what could I continue to do to get better and better approximations for this slope of this blue line? Yeah, why don't we just start using points that are closer and closer to this location at 4? Why don't I use 3 and 5? Well, here's my point 3, here's my point 5. All of a sudden, this slope is getting closer to that slope of that blue line, right? And I can calculate that. I have a slope formula. So whatever this y is, -1, y2 minus y1, x2 minus x1, boom. Now, let's pretend I have some sort of expression for this function in black, and I can find any decimal point at any location. Okay, so like you can just plug it into your calculator using trace or something like that. What 2 points would you want to use to get you a really, really good approximation for what the slope of this blue line is? Discuss with your neighbors. Mr. Ratty, what do you think? What points would I use, Mr. Ratty?
Like 3.999. Right.
Just to the right of 4. Just to the right of 4 would be, so you did 3.999. Right. Why don't I use points like 4.0000001, 3.9999999, and find the slope? I could do that, right? Because I'm not going to get a 0 in the denominator. I'm going to get something very, very close to 0. But that's the idea. Now, we've used kind of the thought process of this, get infinitely close to something, okay? What is the term we've been using to talk about approaching something, but not actually like being at the location? Limits. We're getting infinitely close, okay? All right, well, we have our calculators. We are going to go ahead and find some slopes of some tangents by getting good approximations. And if we don't think our approximation is good enough, we can get better approximations and better approximations and better approximations. Let's start with x cubed minus 2. We are going to focus our attention at x equals 2. I'm going to go pretty quickly through this because it's actually not what we will be doing in the future, but it's going to be used for demonstrative purposes, okay? So just bear with me. Know that it's actually not super important, the actual calculations. The concept is what's important, okay? So let's graph x cubed minus 2. Boom, graph. I'm going to focus my attention at x equals 2, right there. I'm going to find how quickly the function is changing at that location, which is the slope of the tangent at that location. I want to figure out how much. I want to figure out the value, okay? Well, I'm going to start by finding the average rate of change between 1 and 3. Well, I mean, 3 cubed is, I can do this without a calculator. F of 3 cubed is 27 minus 2 is 25. F of 1 is negative 1. Y2 minus Y1 is the change in my Y's. X2 minus X1 is the change in the X's. I get 26 over 2, which is 13. I would say that the slope of this line right here is approximately 13. Do I think it's exactly 13? Maybe. Maybe not. But what can I do so that I know for a fact that it's probably not 13, or it definitely is 13? Go closer. Thank you, Mr. Hinton. Let's take 2 points closer. So we are going to now do it over the interval from, let's say 2.9 to, 1.9 to 2.1. All right, really quick, I'm going to do it. Trace, 2.1, 7.261. Minus, trace, 1.9, 4.859. Divide that by 2.1 minus 1.9. So we do that in their calculator really quickly and tell me what you get. .01. So I said earlier that the slope is approximately 13. Is the slope going to be 13? No, because I just have a better approximation right here because I'm using 2 points closer. The better approximation is close to 12. Now, maybe that means my actual slope is 11. I don't know. Maybe it means it's actually 12. How do I know? What should I do, Mr. Hinton? Let's use closer points. So let's finish off by going to 1.99 and 2.01. If I find the slope between those 2 points, I will know if the slope is probably going to be closer to 12 or closer to something else. Here we go. Let's write down these numbers. 2.01, I got 6.120601. We're going to have to write down that entire number because I want exact values. 6.120601. 1.99, oops, 5.880599, 0599, divided by 2.01 minus 1.99. Please calculate that using your calculator and tell me what it's equal to. I know it's 12.00, but I think it's actually 001. We might have been just rounded a little bit. 0001? I actually did this earlier. 3 zeros. Yep. 12.0001. So, if this is a better approximation, even better than the previous one, and you think if I use 1.999 and 2.001, I'd get a value that's probably closer to 12? Yes. So we could probably, through this kind of analysis, through this procedure, using our understanding, our conceptual understanding of limits, we could say that the instantaneous rate of change of f of x equals x cubed minus 2 at x equals 2 is 12. Going up 12 y's per x at that location. Okay? Let's quickly do this, and I'd like you guys to try this. Using your calculator, find how quickly the function is changing at x equals 1. Okay, and check your slope approximation with a neighbor. Maybe they went closer than you did. Now, if I look at my function, let's go back into the graph. At x equals 1, I can see I have I'm going up. I have a positive slope. I want to try to find the value of that positive slope. Now, your calculators will be rounding. Try not to round your answers, and you will get a value that should be close to a whole number. I'll let you know that. Good. It's because you didn't put your numerator in parentheses. Anybody get any values? The rounding messed us up. So I actually did this earlier. Sometimes our calculators can confuse you. I did this with 1.01 and 0.999. And I got these two decimals, negative 0.969699 and negative 1.029701. So using 0.99 and 1.01, I actually got a value that was approximately 3. Okay, so I think that the instantaneous rate of change, or the slope of the tangent, right, or what we'll call the derivative, of x cubed minus 2 at x equals 1 is 3. And I said that the instantaneous rate of change, or the slope of the tangent, or the derivative at 2 is 12. Okay, cool. Guess why I'm not taking that much time to make sure you guys know how to do this? Because you don't have calculators, and because in the 1600s, mathematicians, they understood the concept of this, but they couldn't do what you just did. They did not have this computational power where they could, by hand, take 2.01 and cube it, then subtract 2, and take 1.999 or 99 and cube it and subtract 2, and then do this calculation. That is a nice computational way to find the slope of the tangent. We did it. Now, if you had calculators for the rest of the year, yeah, you could use this. You could just do this the entire time. But it's not what mathematicians did. They need an alternate approach, and it's not what we are going to do for the rest of the year, because we won't be able to use our calculators all year. Okay? So, no, this is not realistic. The smart people needed to find another way. And what we are going to introduce to you is something that is phenomenal and fascinating, and you might not understand it. And that's okay. Hopefully, if you rewatch the video, you'll be like, okay, I kind of get it now. Okay? All you need to think of right now is that slopes equal change. Okay? And we just found slopes of tangents. Okay? By understanding that if you take 2 points and get them really, really close together, you can find a great approximation of a slope of a tangent. Okay? But here's what mathematicians did. They're like, new way. We need something else. We can't just go 1 point at a time, and I can't use calculators. We're going to pretend this is x cubed minus 2. Okay? And what we're going to do over here is we're going to sketch tangent slope values. This is what I mean. At this point, when x is -2 down here, I'm going to draw a little tangent slope there. Now, remembering that if my pitch is upward from left to right, my slope is positive. We'll use greater than 0 for positive. We could also use like a plus sign for positive. We remember that if my slope is pitched downward from left to right, that your slope would be negative. This is one way to say that it's negative. You could also just say negative. We know that if we are flat, our slope is what? 0. In between positives and negatives is 0. Okay, cool. Well, I'm going to say, okay, this is a positive slope. I'm going to do it here. I'm going to say, okay, this is a positive slope, but it's less positive. And now over here on this graph, I'm going to plot the value of the slope, the tangent slope value, where it's like more positive, less positive, 0 value. This is a less negative. This would be more negative, okay? So I'll say, okay, when x is -2, my slope was positive. When x is -1, my slope was less positive. Okay, go ahead and do the remaining 3 points. We have a point here at 0, a point at 1, and a point at 2. So I got a point here, I got a point here, I got a point here. Now, man, you guys are still kids, and you see some dots. What do you want to do with those dots? Man, I really want to connect those dots. Now, I don't want to connect them just yet. Can we like check and make sure? Can you talk with your neighbors and like check and let's make sure I can connect those dots? Because man, I'm plotting tangent slope values. Like, can I just like willy-nilly connect dots? So please, like, talk with your neighbors. Are you okay with connecting these dots? I like how some people approach it like the way he's phrasing this, it's probably going to be no. So I'm going to go and think that it's no. The answer is
No, absolutely not.
you guys keep talking and somebody tell me yes or no, definitively. Mr. Luce, you say yes. Why?
If you did a tangent line in between the 2 points, it would be in between the 2 dots on that graph.
So if I do a tangent right here, I see the slope is like in between this one and this one, which means my point would be in between that one and that one. Well, is that the case everywhere? Let's see. Oh, yeah. Oh, okay. So this is like, all right. Yeah, that's right. And then oh, yep. Okay, that works. And then, all right. Oh, okay. And if we kept doing that, we would see that. Okay, so, all right, guys, go ahead. Ah, so rewarding. Oh, man. Well, this is actually really cool. And this is what mathematicians discovered. I hope that's not a phone. If it is, I'm gonna burn it. Okay? This is actually a huge discovery. This is so huge, they're like, man, look at this. This is like a graph of some parabola, some sort of x squared graph, where if I plugged in a point, say, 1.5, and I could see the y coordinate on this graph, it will tell me the exact slope of my original function. Okay, think about this. This graph, look anywhere. Okay, right here, boom. This y-coordinate is the exact slope right here. Now this is just a sketch, so it's like exact, yeah, but pretend we're more exact with things, okay? We can get points off of this function to tell us exact slopes of this function at locations. This is the mathematician's alternate approach. They said, if I can find an expression for this function, now they call this function super special, they called it f prime. Okay, this is a little tick mark. It's called a prime. It is like f star. You know how f star was like related to f? F prime is related to f. The original function f, x cubed minus 2. This is its tangent slope function. And they said, man, if I could find the equation for this, I could plug in x's and get slopes of f. Okay? Instead of having to take 2 points really close together and use a calculator, I can just find this equation. Now, finding the equation becomes a little bit more difficult, and we'll find that in a second. But let's go ahead and see, is every single, and this is what we call the tangent slope generating function. This is a tangent slope generator. Gosh, if I can get the expression for f prime of x, I can just plug in x's and I'll get slopes for f. Okay? Now, is all tangent slope generating function going to look like a parabola? I don't know. Let's find out. If this was a function, if this was a parabola, and I sketched its tangent slopes, what would its tangent slope generator look like? Why don't you guys do that right now? So, at the points, boom, 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 sketching tangents, then you're thinking values, negative, less negative. Very good, very good. Negative, less negative, 0, positive, more positive. Oh, okay, so this isn't a parabola. This is something else. But notice it's unique. So it's unique. This f prime, the tangent slope generator function for this is unique to this. And it's some sort of line graph. But it's great. If I plugged in 1.5, I see I got a positive slope. It's more positive than 1, less positive than 2. If I look at 1.5, boom, I got a tangent slope more positive than 1, less positive than 2. And this, if I had an expression for this, would give me a specific value. Okay, let's keep going. Let's see some other unique tangent slope generating functions. See if you can do this one. Please check with your neighbors. Please do this one. Go 1 point at a time. 1 point at a time will help you. Boom, 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 boom. Plot the values of those slopes. Look at your neighbor's graphs. See if they're the same as yours.
Very good.
All right, so this unique tangent slope function is a parabola. It's just like reversed. So this is great. And this is really crucial. This is like the segue into finding the expression. Knowing that they exist. Knowing that there's some equation out there where if I plug in x's into that equation, I'd get tangent slopes of f. A line Well, the slope of a line is consistent, right? So the slopes of the tangents should be consistent. And the slopes of the tangents will just be what the slope of the line is. The average rate of change and the instantaneous rate of change is the same for lines. Lines are boring, but that's cool. So this is just some value. That's cool. This one's tricky. Negative, more negative, really negative. Okay, negative, more negative, really negative. Okay, so it looks like it's like the same thing. It looks like it's trending down to infinity. Really negative, less negative, less negative, less negative. So it's like really negative again. But I don't have a point, so I'm not going to have a slope. Less negative, less negative, less negative. So this is cool. This tangent slope generating function for this function, this 1 over x function, looks something like that. All right, quick test before we move on, and we actually find the expressions, the equations for these tangent slope generating functions, which we now know exist. If this is f, what is its f prime tangent slope generator? It's either A, B, or C. Circle the correct answer and check with your neighbor. Check with neighbors, check with neighbors. All right. We're doing well. Okay. Mathematicians said, okay, this tangent slope generating function, it exists. How can I find the equation for it? Well, they developed a mysterious magical formula for finding the tangent slope to any function at any point, and this will produce our expression, our tangent slope expression. It's not going to make any sense to you, but you will need to understand where it comes from and its translation. They said take any function. Let's focus on this point right here, x. And we're going to take a second point. It's going to be h distance away plus h, giving us an x plus h. Now what we were doing is taking like a point just to the left of x and just to the right of x. What I'm going to tell you is if we take a point at x and then take a second point and put it infinitely close to create a very, very small segment that I connect and extend to give you a tangent line, that it's going to be the same as if I got to the left and to the right. Because as we get closer and closer and closer, the values would approach the same value. So we're actually not going to go to the left and to the right. We're actually going to go at the location and then really, really close to the location. It'll give us the same result. Okay, so what we are going to do is first write down an expression for the slope of this red line connecting these 2 points. Now, if this is x and this is f of x, well then this point is f of x. If this is x plus h, this would be f of x plus h. Okay, the slope between these 2 points would be y2 minus y1 over x2 minus x1. Now immediately I notice x's in the bottom can cancel. Okay. Now I have this formula. And they said, take these 2 points and put them infinitely close together. Now, as the points get closer and closer and closer together, what happens to this h distance? It's getting smaller and smaller and smaller. Approaching what value? 0. Very good, guys. Most other classes would not come up with that 0. Now, what new thing that we've learned in this class talks about getting really, really close to something, but not actually getting there? Limits. They said if you take the limit as h approaches 0, this formula will develop your tangent slope function for any x value, because this line would end up getting flatter and flatter and flatter, and it would end up being a tangent line. There's an alternate approach as well. They would say this is C, and we're going to focus on this point, C, f of C. We want to find the tangent slope there, and instead of this being an h distance away, they just said, oh, make this any random point. And they said, if you find the slope, f of x minus f of c over x minus c, but you have x approach c. So if you get x really, really close to c, wherever x may be, you will also find the slope of the tangent, but now just at a specific location. The formula that they just generated, these formulas that I've just put together for you, they said are so powerful, they're so magical, and they're going to be able to help us so tremendously that we are going to call these the definition of a derivative. Now, we know derivative terminology stands for slope of a tangent. Give me a second, and I'll pause. Okay, derivative means slope of a tangent. They said, here is the magical formula that will give us a function for the slope of a tangent. It'll give us that f prime expression. Okay? F prime of x, this equation, is equal to this formula we just developed. This is the slope of 2 points infinitely close together. Hold on, I'm not done. They have an alternate. Which is also the slope formula of 2 points infinitely close together. This time, not just at any random x location, this time at C. Now, we're going to go back to our friend x cubed minus 2, and we are going to find the equation of this graph. And I will show you a different way to get that the slope of the tangent at 2 is 12, and the slope of the tangent at 1 is 3, which we found using our calculator. All right, here we go. I'm going to find the equation for that parabola that we saw. I'm going to use the magical formula. So magical, they called it the definition of a derivative. You might be thinking like, what? How the heck do we use this? It's actually not that hard. F of x is given to you. I could take f of x and put that right there. F of x plus h is actually not that hard to write. Instead of x, replace x with x plus h. And I have f of x plus h. I could take that, as long as I do it correctly, and put it there, and I can use this magical formula for this function, x cubed minus 2. So let's be careful, and let's plug it in to those spots. I got x plus h cubed minus 2 minus, since I'm subtracting this entire thing, I'm going to use parentheses to be careful. That's over h. Now, the first thing you try with limits, right, is to plug in 0. If I plugged in 0, I'd get x cubed minus 2 minus x cubed minus 2 divided by 0. That's 0 over 0. Now, that is an indication that I do have a limit, but it's also an indication that I need to like simplify this, create this f star to find the location of like the hole, 0 over 0 indicating hole. Let's find the location of a hole. Well, you will find that actually the process that I'm about to do will not be important moving forward because there's an alternate approach, but I'm just going to go through it right now. Now, x plus h cubed, if you remember the binomial theorem in Pascal's triangle, is x cubed plus 3x squared h plus 3xh squared plus h cubed. If you don't remember that, you can just multiply x plus h times x plus h, and then multiply by x plus h again, you get that. Now that'll be subtracting x cubed, adding 2 after distributing the negative divided by h. Thank you. That 2 is gone. Needs to be right there. I appreciate it. Okay. Now, there's a couple things I notice. That x cubed right there, that negative x cubed right there, that goes away. This minus 2 right here, this plus 2 right here, okay, that goes away. The remaining terms all have an h. Well, I'm going to factor out that h. And I get h times 3x squared plus 3xh plus h squared divided by h. Okay, these h's can cancel. Kind of creates this f star. Now, the last thing to do with f star is to take 0 and to plug it in for h. So plug it in here and plug it in here, and I would get 3x squared plus 0 plus 0. My friends, I have developed, using this magical formula, the equation for the parabola that we sketched. Now, the beauty of what we just developed might not be apparent to you. But you told me from before that the slope of this at 2 was probably 12, right? By using your calculator. You told me that the slope of x cubed minus 2 at 1 is probably 3. You did that with a calculator. Well, my friends, I can take this and plug in 2. what do we get? 12, the number we were expecting to get that we found using our calculator. Now this is phenomenal. What about at 1? 3. My friends, this is phenomenal. This is the alternate approach that mathematicians had to use because they didn't have a calculator. They had to find this equation for the tangent slope generator for f. Now this is not the tangent slope generator for all f's. This is the tangent slope generator for a specific function x cubed minus 2. Tangent slope generator for x cubed minus 2. And this might not blow your mind, but it is calculus. This is calculus. This is the alternate approach mathematicians had to find. They had to figure out this equation for this graph. 3x squared. You can plug in x's to this, and it'll give you tangent slopes to this at any location. Pretty cool. What can we do with this? Well, we could also write equations of tangent lines and maybe graph those, and then graph them in our calculator, and it'll look great. Well, let's remember what we need for a line, and we will be using this form. It's called the point slope form of a line. You do not need to solve for y. You do not need to put your equations in y equals mx plus b form. This will be the form of any line we will need for the future. Okay, now we want a tangent line. So this m, which stands for slope, that's tangent slope. So that's 12 if we're talking about x equals 2. Now, if we're talking about x equals 2, that's the x coordinate that we're concerned about. Don't change the x, don't change the y. We need the y and the x for it to be a line. Now, where does y1 come from? Yes, Ms. Hoffman, it is the point on the graph of x cubed minus 2 at 2. My tangent line passes through the point 2, 6. So I need to know that the y coordinate where that slope is occurring is 6. Where do you get 6 from? You plug 2 into f of x. Okay? So x1, y1 is my point. Comes from f of 2, 8 minus 2, 6. This is 6. Now, I do not have to solve for y to graph this. I'm okay with you guys just pushing the 6 over to the right side by adding 6, leaving it like that. You can then, in your calculator, graph y equals 12 x minus 2 plus 6. Oh, beautiful. We just did that. Now, you could have done that already because we already knew the slope was going to be 12 because we used our calculator. But finding this f prime tangent slope generating function, that's the key to calculus, is the invention and the discovery of the existence of this. Okay? Let's do it for x squared. Quickly, with the calculator. Pretend you have your calculator. Find the slope at 3 of x squared. My recommendation is to find the average rate of change, the slope of the secant, using 2.99 and 3.01. Let's go ahead and do that. Yes, use your calculator for this, and then we will not use our calculator for this. And we will get the same answer. But moving forward, we will not be able to use our calculator. So this process, not super important. So I'm going to just do it all in once. I'm going to do 3.01 squared minus 2.99 squared divided by 3.01 minus 2.99. That's nice. That's my slope. Boom. I get 6. Gosh, it tells me it's like exactly 6. It's probably rounding. So 6. Now, I could go ahead and like do 2.999 and 3.001 to see if it like drops and goes to 5. But I'm pretty certain, since I'm like really, really close to 3, that that's probably going to be my slope. And it's probably rounding. All right, let's see if this can be obtained the other way. What is the tangent slope generator for x squared? We already looked at x squared. This is like an x squared up here. Okay, this is the x squared. What is the expression for this line? Let's find out. Maybe it's x. Maybe it's something else. F prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over h. This is f of x. This would be f of x plus h. Okay, let's plug that stuff in. X plus h squared minus x squared over h. It's finding this limit as h approaches 0. I'm going to go ahead and square the x plus h. X squared plus 2xh plus h squared. You will find that this is not important in the future. Minus x squared over h. The x squareds will cancel. The remaining terms have an h in them that I will factor out. So I will be finding the limit as h approaches 0 of h times 2x plus h over h. This cancel. Plug in 0 for this. You guys thought it was x. It's 2x. Now, I said f prime of x is equal to 2x. I said f prime of x is equal to 3x squared before. Well, 3x squared is the unique tangent slope generator for x cubed minus 2. 2x is the unique tangent slope generator for x squared. I found that the slope at 3 is probably 6. What do you get when you plug 3 into this f prime? 6. This is what took until the 1600s to discover. This is what you can easily do with a calculator. Okay? Now, this math here, very tedious, right? Well, mathematicians understood the tediousness of that. And they actually used this magical formula differently. They didn't plug in individual functions like x cubed minus 2 into it and x squared. They just plugged in general functions like a polynomial, x to the p. If I have an x to the p and I plugged it in here, what would happen? They plugged in different functions like 1 over x. They would plug 1 over x to the p, things like that. And what they actually did is not use it this way, but they use this magical formula to develop rules. Okay? To help quickly find the f prime tangent slope generating functions. In the future, we will not be doing all of that messy tediousness, and in the future we actually aren't going to be using the magical formula. It will have been used to develop the rules that we are going to use. And what we will be able to do starting next class is if I give you x cubed minus 2, you will be able to say very quickly, oh, tangent slope generator 3x squared. Using rules, you'll be able to tell me that 4x squared plus 16, its tangent slope generator, 8x. Because the rules, which are generated from the magical formula, are what we are going to use to develop these. Now, we're missing a lot of the beauty, okay? Using rules, we're missing a lot of the great stuff about why this is so fantastic and why the existence of this actually took forever to figure out, because the concept of a limit and an infinitesimal actually took the longest thing for mathematicians to be able to grasp the idea of something being infinitely close to something. It's that limit that really took forever for them to figure out. We don't have to worry about that actually moving forward, because we will just learn rules and we'll be able to say, okay, this is the tangent slope generator. How can I use this to find out more information about that? All right. So, in conclusion, this f prime of x is a tangent slope generator, unique tangent slope generator for f. I can plug numbers into it and I will get a tangent slope. A derivative is a fancy word for tangent slope, which is what we will call the instantaneous rate of change of a function. If I say this function is differentiable, that means it has a tangent slope. We'll talk more about what it means to be differentiable next class. All right? So you are now on par with Newton. Congratulations.